Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So in the last talk, I gave a brief introduction to PCA. In this talk, I'll be talking about our recent work on non-convex robust PCA. I'll explain all these terms in the further slides. And this is joint work with Niranjan, Sujay, Anima, and Pratik. All of them are at different places. So towards the end of last talk, we saw the problem where we observe a matrix M, which is a corrupted version of a low rank matrix, which is L star, and then there is a perturbation or a noise matrix. We denote it with S star. So the example, the case that we considered last time was that we don't know anything about the noise matrix. There was no structure in the noise matrix, and somehow the best we could do in terms of low rank projection was to recover the low rank matrix up to some error, which depends on the norm of the noise. In this setting, we consider a case where the noise is much more structured. In particular, the structure we assume about the noise is that it is very sparse. What I mean is that each row or each column only has a very small number of non-zero entries. And given this summation, so the noisy version of the low rank matrix L star, we want to recover the low rank matrix exactly. So this is the problem. And robust PCA, because if we just do PCA, we'll incur some error, and we want to do it robustly even in the presence of some structured noise to recover the low rank matrix L star exactly without any noise whatsoever. Is the problem clear? Okay, so let me give you an application where this comes up. The application is foreground background separation in a video. So a video is composed of frames. Just vectorize each of the frames. So make each frame as a vector and then stack the vectors one after another. We'll get a matrix where each column is a frame, and each frame has the background component and a foreground component. The background component does not change much over frames. So this is the low rank part of the video, and the foreground part is people moving across, and people moving across or objects moving across or whatever they may be. They are usually sparse because you don't have huge objects that occupy the entire space. So the perturbations in this case are sparse. And if you can do the low rank sparse decomposition successfully, then given a video, we can do foreground background separation, which is helpful, say for instance, in surveillance purposes or something like that. Okay. So the natural formulation of this problem is to write the matrix M as L plus S, where we want to minimize some combination of the rank of L and the sparsity of S. So the zero norm of S corresponds to the number of non-zero elements in S. We want to write M as L plus S, where we want to minimize the rank of L and the number of non-zeros in S. This is a non-convex problem because both the rank function and the sparsity function are both non-convex functions, and we don't know how to optimize this efficiently. So there were these two papers, simultaneous papers by Chandrasekharan et al. And Candace et al., which considered the convex relaxation of this problem, where the rank constraint was relaxed to the trace norm constraint. The trace norm constraint or the nuclear norm is the sum of all the singular values. So if you recall from the previous talk, it's also called the Shatton 1 norm, and it's just the sum of all singular values, whereas rank considers rank is equal to the number of non-zero singular values. So this is a relaxation of the rank function, the trace norm of L, and the sparsity of S is relaxed to the L1 norm of S. This is just as in compressed sensing, where the L1 norm is a proxy for the sparsity of the matrix. And the constraint is the same, M is equal to L plus S. This is now a convex problem, and we can solve this efficiently. By efficiently, I mean in polynomial time. And what these papers managed to prove is that under certain regularity assumptions on the underlying matrices L star and S star that M comprises of, we can indeed, this convex program indeed recovers the true L star and S star exactly. So there is no error whatsoever. if you do PCA without using the structure of S, we will incur some error, whereas solving this problem gives you these matrices exactly without any error. Firstly, I should mention that this problem is the problem of decomposing the matrix into this low rank plus sparse is not even well posed in general. For instance, so we have this low rank plus sparse. So if the low rank matrix itself is sparse, then we could write it as a 0 low rank matrix plus a sparse matrix, or a low rank matrix plus 0 sparse matrix. So the decomposition is not even well defined, so we could have two different decomposition both of which satisfy these low rank and sparse conditions, and the problem is it's not well posed. So the regularity assumptions that make this convex program work, or even in general make the problem well posed, are that the low rank matrix is not sparse, or another way to put it robustly is that the entries of the low rank matrix are all well spread across all the elements, and the mass is all not concentrated in just one element. Put it another way, so if L star is equal to U sigma V transpose is the singular value decomposition of L star, then each row of U does not have a large norm. So in general, each row of U can have norm equal to 1. So let me give an example. So if U consists of orthonormal columns. So if U is say 1 0 0, this is not incoherent because the first row. Yeah. If the U vector is 1 0 0, then the first row has a large norm, and it's so when we take U transpose, the resultant matrix we'll get will be just 1 in the top element and zeros everywhere else, and it's hard to distinguish this from any sparse perturbations. So what we assume about the low rank matrix is that it's not like this, it's more like 1 over square root n and 1 over square root n or something like this. This will ensure that the mass of the matrix is well spread across all the elements, and even if you perturb only small number of elements, the remaining ones will give you enough information to be able to recover the matrix. So that's the incoherence assumption on the low rank matrix. The mu here is the incoherence parameter. And the sparse matrix is degree bounded. What I mean by this is that any row or column of S star has at most d non-zero elements. And so we consider the deterministic setting, and this means that these non-zero elements could be anywhere in the matrix. They are not random or anything of that sort. Under these conditions, Su, Kakade and Zhang proved that the convex program has a unique minimum, and that unique minimum is indeed the true decomposition L star and S star, as long as the number of sparse perturbations d is at most n over mu square r. So let us just try to parse what this means. Say we are looking at very small rank, say r equal to a constant or indeed 1, and if the matrix is optimally incoherent, then mu is a constant as well. In this case, it says that you could perturb almost a linear number of entries in each row and each column, and you are still able to recover the entire matrix exactly without any noise whatsoever. You are introducing huge amounts of noise, but structured noise, and we can still recover the entire matrix exactly without any noise whatsoever.
So it's not just unique optimum, but also optimum matching the actual.
Yeah. The true decomposition is the unique optimum of the program. And this is tied up to constants in the sense that we can construct, there is a constant c such that if d is larger than that constant times n over mu square r, then there exist two different decompositions which satisfy both these properties but are not the same. So you have no way to distinguish which of these is the correct. So the problem is not even well posed. Okay, so we have seen that the problem is, yeah. Yeah. So, so the definition goes via SVD. What is the question? I don't.
I mean, we came to this with the motivation from the foreground and background image that you had shown.
Yeah.
So we want the low rank matrix, the L.
Yeah.
Correct. Let's say I append all the images as. Do you need any structure in the image? I guess the question is, what is the physical interpretation of the background being incoherent? The background being matrix. What would it correspond to?
That would correspond to the background being reasonable and not just one person here, one person there, or something like that. So the background somehow occupies the entire scene and not just a person standing here and a person standing there. No. So if there is if the matrix satisfies these conditions, it's not necessarily true for every matrix. If the matrix has such a decomposition which satisfies these two conditions, then you will be able to recover the decomposition. If there is no such decomposition, you can run the algorithm, it will give you something, and then you will realize that it does not mean anything.
Does incoherence mean that the amount of foreground is very less? Like we have sufficient amount of background?
Yeah. So foreground corresponds to the sparse perturbations, which means that you don't have too much traffic in the video. There is only a small amount of video, and there is a background, good enough background that's yeah. Okay. So yeah, here we said that the convex relaxation algorithm solves this problem up to constants optimally. So what is there to be done here? So the issue with the convex relaxation is that its runtime complexity is cubic per iteration, and it does not scale to large sizes. Moreover, to get an accuracy of epsilon, the number of iterations we need to do goes as 1 over epsilon, and this really does not scale well for very large size problems when you want good accuracy in your result. So what our work does is to propose a new non-convex algorithm which does not go through the convex relaxation route, but rather tries to solve the original rank and sparsity constraint problem. And this algorithm has a complexity of r square mn per iteration. So r is the rank here and m and n are the ambient dimensions. Just doing a PCA will take order of r mn time. So this complexity is just a factor of r away from the complexity of standard PCA. And usually r is small. So this should be close to the runtime of the actual PCA algorithm. And our algorithm also has geometric convergence. What I mean by that is that to obtain an accuracy of epsilon, you would need to do log 1 over epsilon iterations of the non-convex algorithm that I am going to describe. And the algorithm actually probably recovers the same pairs of L star and S star that convex methods do. So we get the same optimal recovery results, but propose a much faster algorithm than the convex relaxation technique. Yeah.
There is no issue of, is there an issue of local or global optimality, like since it's a non-convex optimization?
Yeah. So we don't look at it in terms of how the function space looks like or anything of that sort. What we can show is that whenever you have a true decomposition of L star and S star, the algorithm indeed converges to L star and S star. So we are not making any claims about whether or not there exist other local minima, saddle points, or anything of that sort.
How does this function look like this non-convex?
I mean, the function we are essentially trying to minimize is this rank of L plus the sparsity of S subject to m equal to L plus S. So let me now describe the basic algorithm. At each iteration, we maintain an estimate of the low rank part L and the estimate of the sparse part S. And each iteration consists of two steps. The first step, we look at m minus S. If we had S exactly, then M minus S should indeed be low rank. But we don't know S exactly, so M minus S will only be approximately low rank and not really truly low rank. So we project M minus S onto the set of low rank matrices, so that's PR, the projection onto the rank R matrices. We make it, we update L to be that, and now we take this L and look at M minus L. If L was exact, M minus L should be sparse, but M minus L is not sparse because L is not exact. So we threshold all the small elements to 0 and only retain the largest elements, which will make S sparse. Sorry? Yeah, so initially we start with say S equal to 0. S is all identical equal to 0. So we have a fixed initialization S equal to 0. Yeah. Under these conditions, it will be unique. There will be unique decomposition satisfying both these conditions because there are all these algorithms which will recover that decomposition. And if there were two, they should recover both of them, which should exactly be the same. There is a fixed initialization S equal to 0 for this, and for even the convex relaxation, there is a unique optimum at L star and S star. So there cannot be two different L star and S stars. Right, so we keep repeating both these steps till a fixed number of iterations, till we feel we have converged. And the main idea in this approach is that instead of tracking the L2 norm, the operator norm or the Frobenius norm as we did in the previous examples, in the last talk that I mentioned, we'll track the L infinity norms of L minus L star and similarly S minus S star and show that they decrease in each iteration. R is the rank of the underlying matrix. So in practice, you could keep trying various ranks and see which you will do a cross validation. So you set a particular R and then see how that works. If that does not work well, then you go to the next R and so on. That's only dependent because the number of iterations okay, so this is a very basic version. There are further versions which depend on R square in a particular way. The L infinity norm is because so when we begin, we know that the low rank matrix has elements spread all across the matrix. But when we take the PCA, it's not, if we just get L2 norms on the error, we don't know if the recovered matrix, the errors are concentrated on just one element or they are spread all across the matrix. Taking just L2 norms will give you, so just taking L2 norms will not give you the fine-grained information about the structure of the errors. So it will only tell you that the aggregate error is so much, but you don't know how the error is distributed among all the elements. But when you take the L infinity norms, you get error on each of the elements in particular, and this gives you a much fine-grained information on how the errors are propagating. Yeah. So okay. So what this means is that we set all the elements of M minus L whose absolute value is less than this threshold to 0, and I haven't specified what that threshold is, but I'll specify later. Why will it be a column? It'll be a matrix, right? No determinant. So you start with S equal to 0. So you get an L. You compute M minus L. It will be a matrix, and you have a threshold zeta, and you set all the elements of this matrix with value less than zeta to 0. So that can be done by, say, the power method, or there exists very efficient algorithm for computing the top R principal components of any matrix. Yeah.
So how did you argue that L star and S star is unique?
L star and S star satisfying those conditions are unique because the regularity conditions that I mentioned. These two conditions. Because, so take any such L star and S star. At least from this result, we know that the unique optimum of the convex program is going to be that L star and S star. If there were two of them, both of them should be the unique optimum, which means that they should be equal.
And each of those two steps there are actually solving pieces of that convex program as well. That's why you are saying that it should converge to that L star, the same L star.
So the analysis there does not really depend on the algorithm. It just says that once you write down this convex program, we can write down the conditions for the optimum. So it will be the KKT conditions.
Right. Now what I'm saying is that the alternating minimization approach
Yeah.
is solving that problem. Given an S, it's solving. Given an S, it is solving for the M. That solves that optimization problem and vice versa. So you are actually trying to solve that the convex relaxation problem.
The non-convex problem. Because we are projecting directly onto the rank constraints. We are not trying to minimize the trace norm. We are just trying to directly minimize the rank and the sparsity. So we are directly trying to solve the non-convex problem. Okay, so let me proceed. Okay, so the basic lemma we use, which is very reminiscent of the last exercise we proved in the last lecture, is that if you have a low rank matrix L star and the sparse matrix S star satisfying the previous, so L star and S star satisfy the regularity conditions, and if L is the rank R projection of L star plus S star, with each of the elements of S star not being too large, then we get an infinity norm bound on L minus L star, which is 1/4 of the infinity norm of S star. So just to recall, the bound we had earlier was that and compare that to this, where we have infinity norms in both the places. The maximum element in the matrix, maximum absolute value of the element in the matrix. Okay, so let's see how this proves the lemma. So we recall that, okay, so we'll show that if we have this step, then for the next step, the errors that we'll be incurring will decrease by a factor of half. So this is an iterative procedure. What we'll show is that in each iteration we'll decrease the errors by half. So S is said to be this thresholded version of M minus L. Let me specify what the threshold we choose will be. It's just it's just exactly the same as the bound we get on L minus L star infinity. Once we set this threshold, we have two guarantees. One is that the support of the sparse matrix that we recover S is contained in the support of the true sparse matrix S star. So this is because if a particular element of S star were equal to 0, then M minus L would just be L star minus L. And by this guarantee, it's smaller than 1/4 of whatever that quantity. And the thresholding operation sets it to 0. So the support of S is contained in the support of S star. So our estimation of the perturbation never goes beyond the actual sparsity. And a similar argument also tells us that we indeed estimate S star up to an accuracy of half of what we initially know it is. Just using the thresholding, the choice of the threshold and the guarantee on L minus L star to be smaller than the threshold, we can argue that the estimation error in S star is going to be at most half of what it initially was. Now in the next step, we are going to apply the same lemma to PR of M minus S. Right? So this is the next step, that we estimate the low rank matrix L to be the rank R projection of M minus S. And M minus S now is L star plus S star minus S. L star is the same low rank matrix. S star minus S has the same sparsity pattern because the support of S was contained inside the support of S star. So we have the same conditions on the sparsity of S star minus S. Moreover, we have decreased the infinity norm of S star minus S by half. Right, so we can apply this lemma. So when we applied this lemma to the next step, you would have decreased the sparsity of the value of the sparse perturbation to half of what it initially was, and each of these iterations then keeps decreasing the error by half. So yeah, S is equal to 0. So that's why we are doing PR of L star plus S star. So it's just PR of M. So let us see why proving something like this is why this does not follow from standard results. The sparsity of S star along with the infinity norm of each of the elements actually gives us a bound on the operator norm of S star. This can be proved just using Cauchy-Schwarz inequality. And then, as we saw earlier, Wales inequalities tell us that the spectral norm of L minus L star is at most the spectral norm of S star. This is indeed just the triangle inequality as well, at least in the first step. And similarly for the Frobenius norm. But obtaining bounds on the L infinity norm are much harder, and we require L infinity norms here because there is much more structure in the data that we have to leverage if we have to get exact recovery as opposed to only approximate recovery. Okay, so if there is anything to take home from this talk, it would be maybe this slide and the next. So I'll explain how we obtain the L infinity norm bounds, and I think this may be useful in general context as well. So let me try to go over the proof in the rank 1 case. So L star is U star transpose. So L star is just rank 1, and S star is a sparse perturbation matrix, and we are projecting it again to rank 1 matrices, which from which we get L, and let's say this is equal to lambda UU transpose, where lambda is the eigenvalue and U is the eigenvector. What do we get from standard results? Firstly, the sparsity of S star means that we get a bound on the spectral norm of S star. Say it's less than, say, very small number 0.1. This then gives us, just using triangle inequality and Davis-Kahan, that lambda lies between 0.9 and 1.1, and U star transpose U is at least 0.9. So U star and U are almost aligned, but we don't exactly know how they differ in the L infinity norm sense. Okay, so we just write the eigenvalue equation for the matrix U star transpose plus S star. So this times U is equal to lambda U. This is just the eigenvalue equation. So rearranging terms gives us I minus S star over lambda times U equal to U star transpose U over lambda times U star. Right, this is just rearranging the terms. And we know that S star is at most 0.1 and lambda is at least 0.9, so this matrix I minus this thing is invertible. So we take it to the other side and we expand it using just Taylor series. Okay, so this is the same equation that we had on the previous slide. So the very nice thing about this is, so firstly it's not explicit equation for U because U appears on the right hand side. But the very nice thing about this is that the place where it appears on the right hand side is just as inner product between U star and U. And standard results tell us how to bound this quantity because it's just how close U star and U are going to be. But apart from U star transpose U, everything else is explicit. So the right hand side does not contain anything about U. Now the sparsity of S star and incoherence of U star, so these are the properties that we assume. These give us infinity norm bounds on S star to the P times U star. Now all we have to do here is apply triangle inequality, and the L infinity norm of U will be this will be a constant because the numerator and denominator are bounded, and so the L infinity norm of U star and S star U star, S star square U star and so on, and S star to the P U star is decaying as half to the P. So all of them sum geometrically. So just using this inequality, it's very easy to deduce infinity norm bounds of U, U minus U star and any such quantity.
Sparsity of S star depends on the D, right?
Yeah, yeah. And we had that assumption on D less than n over c mu square, Cn over mu square r.
So you're using that information?
Yeah, so whenever I said, yeah, so we are using the fact that D is less than n over mu square r because U star has the mu square r and so on. So, yeah, just to reiterate, the only thing that we used on the right hand side is from the classical results is Davis-Gahan type bounds, where we get results on the perturbation of the eigenvectors in the L2 norm, and we use that and then further structure on the matrices that we are involved with, and this lets us get infinity norm bounds, which are much stronger than just L2 norm bounds. Okay, so yeah, this is a restatement. This is the same lemma that we saw earlier, but there is still one issue with this, and the issue is that we assume that the infinity norm here is smaller than some quantity times sigma r, and when we are given a matrix, we don't know why this should be true or how can we use this, right? Okay, so I'll tell you what we can do in the first step. So L star is incoherent, so let me write down. So L star was U star U sigma V transpose, and so any element of L star ij equals the row here times the sigma matrix times the column here, and this we know was bounded by mu square root r over n, mu square root r over n times the maximum element here is sigma 1, so this is less than or equal to sigma 1 mu square r over n. Whereas what this requires is we want the S star infinity to be less than mu square r sigma r over n, which could be much smaller than the sigma 1 here. So given the matrix, we know that the maximum element of the matrix is bounded by mu square r over n times sigma 1. So we can threshold all the elements of the matrix so that every element is, the maximum is still sigma 1 mu square r over n. In that case, the perturbations cannot be larger than 2 sigma 1 mu square r over n, and so that is the case. We have this general lemma. So okay, let's say we have a rank R matrix, but we are doing the projections only onto rank K. We require S star infinity to be only smaller than mu square r over n times sigma K, and we essentially have the same result as we had before, plus the error due to the remaining components K plus 1 to R. So in particular, when K is equal to 1, all we are assuming about S star infinity is that it's less than mu square r over n times sigma 1, which we know how to achieve by just thresholding all the elements of the matrix. We do the projections onto rank 1. That will give us this guarantee on the rank 1 projection, and right when this S star infinity, right when the error is comparable to mu square r over n sigma 2, we'll go on to the next stage, take K equal to 2 and apply this, do rank 2 projections and then apply the same lemma. So we keep refining at each step, getting one dimension at a time. Yeah.
But to the threshold, you still need to know what sigma 1 is.
Yeah. Yeah. Actually, we don't exactly need to know the exact value. All we need to know is a bound, and we can get a estimate on the bound by just looking at. Okay, so we just need mu square r sigma 1 over n, and this indeed can be replaced by the maximum element of the matrix. So that can be gotten easily just by looking at the matrix. Okay. So is this part clear? So this was a direct rank R version where the matrix was rank R and we were doing rank R projections. This is a more, this is a finer version of the same lemma where the matrix is still rank R, but we are doing projections only onto rank K. We have a weaker assumption because since we are doing projections onto rank K, but we have this error incurred due to ignoring the components from K plus 1 to R. Okay, so this is the algorithm I just described. So for K equal to 1 to R, we try to get one component at a time, and for each component we do projections onto the set of rank K matrices, and the threshold is chosen appropriately again, depending on the lemma that we saw earlier. And for each k, we run these iterations log 1 over epsilon times, and at the end of it, we are sure to have decreased the error up to epsilon or up to the next up to sigma k plus 1. Then we go to k plus 1 rank, and then keep repeating this procedure to rank R. So that is the maximum you need to. You may converge earlier as well, but once you. So what this lemma tells you is that you will decrease the error in L minus L star up to this number. You cannot go beyond. And if this number is much, so since your desired accuracy is much epsilon, if this number is much smaller than epsilon, you don't really care. So once you run log 1 or epsilon iterations, either your error is equal to epsilon, or your error is this much. So log 1 over epsilon is because we have this halving, and if this is much smaller than epsilon, we only need to go to epsilon accuracy. Okay, so this was the algorithm. Yeah, so the final theorem is that if L star is mu incoherent, rank R, and S star has at most n over phi 12 mu square R, explicit constant, then in each iteration of our algorithm, the support of ST is contained in the support of S star. ST minus S star at the end is going to be at most epsilon over n, and LT minus L star in each element is going to be at most epsilon over n. Okay, so let's see how this compares to convex solvers. The inexact ALM is the fastest and most widely used special purpose convex solver for this problem. And what it does is it tries to solve the convex problem by trying to alternately project onto the set of onto the trace norm ball, which means that the trace norm is equal to certain number. And again onto the L1 ball. So it keeps alternating between these two convex projections. The issue with this is that even though the final matrix that we are going to recover is low rank, the intermediate iterates could be high rank whenever you project onto the trace ball. And that is the main reason for the growing complexity of this method. So n alpha, so this plot projects the maximum rank of the intermediate iterate, and the x-axis represents the number of non-zeros, maximum number of non-zeros per row or column. So as we increase the number of non-zeros in our data matrix, as we are corrupting our matrix more and more, the intermediate rank of the IALM goes beyond 600, for instance, even though the true underlying rank is just 5. So in most of the special purpose convex solvers with trace norm minimization, the biggest issue is that the intermediate iterates could have very high rank, which leads to both storage issues and time issues, because you are having to do a much larger SVD as opposed to our method where we only do rank R SVD. Okay, and this is a comparison of speed for alternating projection, which is our algorithm, and inexact ALM, which is in the red. The first plot shows time versus the number of corruptions per row or column, and the second one shows time versus the incoherence parameter. And in both cases, our algorithm runs much faster than inexact ALM. Okay, so let me show you this example. So this is, I think, a shopping mall or something like that, and so the first on the top left is the original video, and the bottom is the low rank component, which should correspond to the background, which is gotten just by doing PCA. And the second column, so the top is the low rank part recovered by our algorithm, the bottom is the sparse part recovered by our algorithm. The third column is what is recovered by convex relaxation, background and foreground. So the video is maybe for a minute or so. I'll run and you can check. So just the vanilla PCA has much more noise than either of these two backgrounds. So and it's hard to distinguish between, at least I find it hard to distinguish between these two, but the only thing is that our algorithm, so our thing runs much faster than the convex relaxation technique.
So any explanation why the shadows are being picked up in the background?
I mean, they are not exactly low rank, so
If they're closer to low rank than sparse.
so if you want exact low rank, maybe you need to go to a much higher rank. So this is by using rank equal to 5 or 7 or something like that, a very small number. Okay, so to summarize, what I presented is a simple non-convex algorithm for doing the robust PCA problem, where the robustness is getting rid of sparse perturbations, and the algorithm consists of alternating non-convex projections. Non-convex because we project alternately onto the set of low rank matrices and sparse matrices. We saw that our algorithm is factor r slower than vanilla PCA. This is because we have r different rounds and each round just does one PCA. So since there are r different rounds, it's factor r slower than vanilla PCA, but it is much faster than the convex version of the robust PCA whenever the rank is much smaller than the ambient dimension. And a meta goal of some of this work is to design faster non-convex algorithms for solving machine learning problems. In many cases, in recent work, we have seen that people have come up with convex relaxation techniques for solving non-convex problems under certain data assumptions on the input, and it's not clear if we really need to go to a high dimension, relax the problem into a convex problem and try to solve it. We can indeed try to solve these problems under the same regularity assumptions in the non-convex regime, and in many cases we have been able to show that these non-convex methods indeed recover the true matrices up to similar accuracy as the convex relaxation techniques. Yeah, I think I'll stop there. Thanks. Yeah.
So just to understand video example that you model, is it assumed that the background is constant across the video sequence? Or
No, it's not constant. So it will be constant at least across a reasonable period. So it will be, so you can see a person coming back, going away and standing back again.
So in other words, you actually have a sequence of M matrices, right?
No. So each of these, so this is a frame. You put this in a long vector and you stack all of these one side by side. So that will be your matrix.
So that is, so you just have one matrix. Of
One
the
matrix.
entire video sequence.
Yeah. And each column corresponds to one frame. The assumption here is that the background frame does not change too much over multiple columns. So the background frames correspond to the low rank part because they have more mass here, whereas the foreground part keeps moving, is very varying across multiple frames. So they are the sparse perturbations.
So this is like a batch processing where you take the entire video.
Yeah.
and process it one shot. So can I ask one more question? So I'm only familiar with very little work in this area, but I know one work on this thing called it's called reprox, robust reprox. This is from Namrata Vaswani at Iowa State.
Okay.
I don't know if you're familiar with
I'm not familiar with the work.
She talks about online versions of these algorithms instead of batch processing.
Okay.
And so, if you're not familiar, then
Yeah, maybe I should take a look at the. Thank you.
More questions?
How about the scenario where the background is more fast moving, like suppose you are in a moving train or something, and here you have a monitoring camera. So there, I guess the background is more fast
Yeah.
compared to your stationary object.
Yeah.
Or you would have a mix of things like
Yeah,
just
yeah,
between the compartment versus the background.
yeah, yeah.
So same thing can work, or
I don't know how this would work in such a setting.
Yeah.
machine learning scenario like as you mentioned, we generally use the surrogate loss functions for approximating those non-convex functions like a zero loss function. So can you pinpoint some like papers that are good for reading and like about these non-convex techniques, like optimization techniques?
You mean how to choose the surrogate loss functions, or?
Surrogate loss functions generally are convex functions.
Yeah.
Like as you mentioned, like there are non-convex optimization techniques that directly solves the
Yeah, yeah.
like the ML problem in
Yeah,
ML.
yeah.
So
I mean, so the non-convex version has been very recent, so I don't know of a survey of any of those works, but I can send you a list of papers which does non-convex optimization.
thank you.
For the compression, no, I don't know if this model is relevant for compression of videos. Yeah. So maybe once you know the background part is low rank, so it automatically gives you compression because M is an n square matrix, whereas the low rank part and the sparse part have very succinct representations. So, but I don't know if people have used this for compressing videos. Yeah, that's a good point. I'm not sure. So this is a standard test set which is available on the web. I don't know how they generated it and all those things. So this is one of the standard test sets that are available for background foreground separation. So this is available on EMA's website from UIUC. I can point you to him. This and many other videos are available for this task.
Okay. If there are no more questions, let us thank Praneeth for encouraging us to think non-convex. And we thank him with a token of our appreciation.
Thanks, Aditya.